Okay, in section 1.2, we want to look at graphs of equations. Well, given just a set of points, it should be fairly easy for us to graph an equation. And so we know that the graph of an equation is a set of all points that are solutions of the equation. So if you're just given a table of values, that's easy enough to plot those points and look at the graph. Let's take a look at this table, however, and let's take a look at the finite differences of the points. So if I'm looking at the x's here, as I travel down here, I look at the difference from an x of 1 to an x of 2 is a positive 1. And then from 2 to 3 is 1, 3 to 4 is 1. At the same time then, as the x is increasing by 1, the y is dropping by 3. All right, so this guy from 1 to negative 2, this one is also dropping by 3, and so is this one. So if we have a constant rate of change, the change in our y is changing at the same rate the change in the x is, then we know that we have a linear function. Okay? Well, yeah, we can plot those points, but let's see if we can come up with the equation of the line and then graph it from that. So we know that the rate of change is a negative 3. All right, well, that's one thing that will help us graph a line. The other thing we need to know is where's the initial point? Where does it start on the y-axis, or where the x is 0? Okay, so where the x is 0, then I left a little spot here on our chart. Well, if we work the way from the bottom of the chart up, we see that as the x's drop by 1, from 1 we go to 0, what happens to the y's? Well, the y's then are increasing by 3. So from 4 up here, we would have to add 3. Okay? So the initial point is 7. So our equation then is y is equal to, the slope is the rate of change, so negative 3x plus 7. So the initial value is at 7, and the rate of change, we're dropping 3 and going to the right 1. Dropping 3 to the right 1. And that's another way to graph that equation there. All right? Okay. Another thing that we're going to talk about are the intercepts of a graph. So let's start off with this graph. Let's say I have a curve that looks like this. All right. Well, if I want to look at the y-intercepts, I want to know where is it crossing the y-axis here. Well, this particular graph doesn't have any y-intercepts because it's not, x-intercepts because it's not crossing the x-axis at all. Whereas y-intercepts, where it crosses the y-axis, we have 1. Okay. Now let's take a look. Here's another curve. Let's say we have this curve. Maybe you know what the equation of a curve like this would be. Okay, and if you said cubic, that would be right. Let's say we want to know how many x-intercepts this has. So where it's crossing the x, 1, 2, 3 spots. So this curve has 3 x-intercepts, whereas where it crosses the y is only 1 time. So it has 1 y-intercept. All right. Another possible curve we might be looking at is, how about one like this? So we have a parabola or a quadratic that's quadratic in y, and when I look at the y-intercepts, x-intercepts, sorry, here's the x-axis, the x-intercept, we only have 1. The y-intercept, where it crosses the y, we have 2. So we can see from this information alone that it is not a function, because for every x we have more than 1 y. And then another graph that we are going to look at is a circle. So how about if I put the circle up there? So in this case, for the x-intercepts, it's not crossing the x-axis at all, And for the y, it also has no y-intercepts. Okay? Now, let's say that we want to find the intercepts. Okay? We want to find both the x and the y. Well, when we're looking for the x-intercepts, we are looking along the x-axis. And along the x-axis, all our y values are 0. So, to get the x-intercepts, we plug in 0 for y, and then we solve it. Okay, so we have 0 is equal to x cubed minus 4x. All right, when we're solving something like this, it's not a simple equation. We want to find, we know that we can have up to 3 zeros because it's a cubic equation. So our first thing we want to look for is what do they have in common? What can we factor out? Well, I can factor out an x. I'm left with x squared minus 4. And then I see that x squared minus 4 is a difference of squares. So we factor that into x plus 2, x minus 2. So I've got 3 different factors. So my x-intercepts are at 0, -2, and +2. And if I thought of them as ordered pairs, it would be 0, 0, -2, 0, and 2, 0. Okay, so those are the x-intercepts for that one. All right, over here, for the x-intercepts for this one, well, we do the same thing. To get the x-intercepts, we plug in 0 for y. So x minus is equal to 0 squared minus 3. So the x-intercept is -3. We only have one x-intercept there. So the x-intercept is at -3. Or that point would be -3, 0. All right. For the y-intercept, we do just the opposite. We plug in 0 for the x. So if I plug in 0 for x, 0 cubed is 0, minus 4 times 0 is 0, so we get a y-intercept of 0. On this equation over here, we do the same thing. We want the y-intercept. We plug in 0 for x. Solve it for y. So we would add the 3 over, and then take the square root. Remember, when we take the square root, we have to do a plus or minus the square root of 3. So in that case, we have 2 y-intercepts. Circles. Okay, well, we want to talk about the equation of a circle, just a good reminder again. From geometry, you know that the definition of a circle is a set of points a given distance from a given point. So our given distance is our 5. Our given point is the point 2, -3. So let's say this right here is the point 2, -3. And I want all of the points that are exactly 5 units away from that. Okay? So for example, maybe this point is 5 units away. Here would be another point that is maybe 5 units away. So if I plot all of the points that are 5 units away, we end up with a circle. And the 5 represents the radius. So our radius is 5, and the center of the circle is the given point that we started off with. So we wanted all points that are 5 units away from the center point to -3. Okay? So to write the equation then, we need the distance formula, because we want this length to be 5 And out here on the circle represents any point x, y that is 5 units from the point to -3. So we are looking at the distance. We're looking at the distance between the point to -3 and any point x, y. So remember our distance formula? It's derived from the Pythagorean theorem, but we need the difference in the x's. So the difference in your x values, we have x and 2, so it could be 2 minus x or x minus 2. I'm going to choose to write it as x minus 2. That is the horizontal distance between those points, so that might be the a value of the Pythagorean theorem. So we need a squared plus, we need the b squared. The b is going to be the vertical distance then. So to get the vertical distance, we look at the difference in the y values. So the -3 and the y. So to get the distance, we subtract. It could be -3 minus y, or it could be y minus -3. And I'm going to choose to write it that way. Why am I writing a plus? Because y minus -3 changes it to a +3. That's our other leg to our triangle, if we would draw a triangle. So that squared plus this squared is equal to our radius squared, the distance, the hypotenuse squared. So our hypotenuse would be our radius. So it's equal to c squared. Okay? Well, that then is our equation. All we're going to do to simplify that is just change that 5 squared to a 25. All right, so look at our equation here. X minus 2 quantity squared plus y plus 3 quantity squared is equal to 25. Now notice the numbers in there. We have the x and the y, but then we have a -2 and a 3. Now think again, where did that -2 and 3 come from? Oh yeah, it came from the center point, except we want to do distance, so notice how the signs are changed. The 2 became a -2, the -3 became a +3. And where did we get the 25? The 25 came from the radius being squared. So it's equal to radius squared. So our equation of the circle is x minus h quantity squared. And what do you suppose the h stands for? Oh yeah, it's the x value of the center of the circle plus, whoops, I don't know what I was doing there. So I need a parenthesis, y minus k squared. And what does the k represent? Oh yeah, it was the y value of our center, is equal to, where did 25 come from? Oh yeah, it came from squaring the radius. Okay, so there's standard form for the equation of a line. And what's nice about standard form is that you can see the center and the radius of the circle. All right. Well, sometimes our circles are going to be in general form. So here's an example of general form. And general form is where everything has been multiplied out and like terms are combined. Okay, well, we need to get it back to the form where we can find the center of it. Because, boy, looking at that equation, I have no idea how big that circle is. I don't know where it's placed at. So we got to get it back in standard form. All right, so we want to put the x terms together. So I see a 4x squared here. I'm going to lead off with that guy. But then I'm going to go over and find another term with an x. All right, there we have a 20x. So I'm going to move it over here. Okay, then I'm going to leave a little bit of space here, and then I'm going to pull down the y squared. So 4y squared, and then right after it, I'm going to put the y term. So I'm going to put the -16y here. Okay, and then I've got this 37. Well, what we're going to do with the 37 is move it to the other side for right now. So it's a positive 37 on the left side. So when I move it to the right side, it's going to be a negative 37. All right, well, to get it in The standard form, let me go back here again. Notice that we have to have a quantity squared. We got to complete the square in the x and the y. Okay, so that's our next job. So to complete the square, we cannot have a leading coefficient here. We got to get this 4 out of the way, or otherwise I'm not going to be able to complete the square. Well, I noticed that a 4x squared and a 20x, I can bring that 4 out of both of those. So I'm going to factor that 4 out. And even if it's not, it doesn't go in there evenly, you know what, you still have to factor it out. Maybe it's a 3x squared and a 20x. You know what, bring that 3 out anyway. So this time, though, I gave you some nice, neat numbers to work with. So I've got x squared plus 5x. All right. Now I'm going to leave a little bit of room so that we can complete the square, so I'm going to put an end parenthesis over here. And then I'm going to do exactly that same thing to the y's. I got to get rid of that 4. I am going to multiply, or I'm going to factor it out. So I gave you a problem where it factors out nicely. That's not going to happen all the time, though. So I get a minus 4y. Then I'm going to leave some space and continue on down, bring down that negative 37. Now I can complete the square. X squared plus 5x plus what? Oops. Ignore that. Let me see if I can get an eraser. Get rid of that point. No, darn, it's not going to do it. Okay, well, ignore that. It's just a 5. Sorry about that. All right, so to complete the square, I need half of this value squared. Half of it squared. Now, my pointer's not working. Okay, so to complete the square then, I go x squared plus 5x. All right, so the number that we have to add inside the parentheses to complete it, we take half of 5, so that's 5 halves, and we square it. When you square a fraction, you square the numerator and the denominator. So 5 halves, whoops, becomes 25 fourths. All right. Now, I can't just arbitrarily add that to this side. So 25 fourths is on the inside of a parenthesis that has a 4 on the outside. Because it's on the inside, that means that 4 has to be distributed. So 4 times 25 fourths is actually 25. So over here on the other side of the equation then, because I added 25 here, I also have to add 25 over on this side. So I'm going to make it a little 37 because I have totally run out of room, and I'm going to put plus 25 here. So that plus 25 came from what I just added here. It looks like 25 fourths here, but after I distribute the 4, it became a plus 25. So I do the same thing to the other side of the equation. With the y squared, to complete the square in y squared, I look at that coefficient of the y term, the negative 4. I'm going to take half of it and square it. So half of negative 4 is negative 2. A negative 2 squared is a positive 4. Now remember, you're always squaring this number, so it's always going to be a positive. All right, well, I see a plus 4 here, but I also have a 4 on the outside of the parentheses. When I distribute through that 4, that gives me a plus 16. So because I added 16 over on the left side, I'm also going to add 16 on the right side. All right, the reason for doing all of that work is so that we can write these as quantity squared. So this is x plus 5 halves quantity squared. Here, the 4, I have a 4 on the outside of the parentheses, but the quantity squared would be y minus 2. That's just your factoring process. We're factoring it down. And then I want to combine all of these numbers here. So we've got 25 plus 16 minus 37. So that's going to give us 4. Oh, doesn't want to write much anymore. So now I have it in standard form. Okay? So I have it in standard form. So then we can see from this standard form what the center of the circle is. Any guesses? Well, if you said negative 5/2, positive 2, you are correct. That's the center of our circle. All right, we also want to find the radius. Well, I've got a 4 over here, but notice that I also have these 4s right here, and we don't want those there. That's not back. Once again, let's take a peek at our standard form here, and we don't have variables in front of the quantity square, so that we have got to get rid of those. So we have got to divide by the 4s, and when I divide by the 4s, that'll turn this into a 1. So remember that there is our radius squared. So if our radius squared is equal to 1, then our radius is 1. So we have a small circle here with just a radius of 1. All right, so that is, we went from general form, this form right here where it's all multiplied out, to standard form. And standard form is the form where you see the center and the radius of your circle. Okay, I know this is getting long. We're at 22 minutes. Got a few more things to do. Points of intersection. So I have these two graphs here, and I want you to find the point of intersection. Well, you could always graph at it and see what they are. But the point of intersection is, of the two graphs, is an ordered pair that is a solution point of both graphs. All right, so to find that, we can set them equal. So in this case, I already made it kind of simple because both of these equations are in terms of y. So we want to find where they're equal. So we know that y is equal to y, so we're going to set the two equations together. So we're looking for where x squared minus 3 is equal to x minus 1. All right, I have only an x squared on one side, so that means I'm going to have to bring everything over and factor it. So that's how you find the points of intersection. So I'll just take you through this quickly then. I move the x over, minus x. I add the 1 over, minus 2. And we were looking for the points of intersection, so you're looking for an x and a y, where the two are equal to each other. All right. So this will give me the x values. So if I factor this, I get x minus 2, x plus 1. So that means either x will equal 2 or x will equal negative 1. Well, I'm not done with that yet. That gives me the x values of the points. We're looking for the points of intersection, so we need an x and a y. All right. A clue here is that when you substitute these in, normally you go back to the linear. In this case, if you go back to the quadratic, you're just going to get one value. But like if you had a circle, sometimes you could get several values. So go to the smaller equation. So instead of the quadratic, we'll use the linear. All right, so we're going to plug the 2 in for the x here. So y is equal to 2 minus 1. So the y value is 1 when the x is 2, and then we're going to plug the negative 1 in for the x in the linear function, and we get negative 2. So those are our points of intersection. Now, the way we're going to use this is to look at a break-even analysis. And a common business application that involves points of intersections are break-even analysis. And usually the marketing of a new product requires an initial investment. So we need to know then, when we've sold enough of our whatever units that we want to sell, when we've sold enough of them to break even. Okay, so we're looking for a break-even point. Well, the total cost of producing so many units of a product is known as the cost function. And the total revenue from the sale of X units is referred to as the R for the revenue. So if we want to find the break-even point, then we set the cost function equal to the revenue function. Okay? So we want to know when we're going to break even. Anything above that then we make a profit. All right? So let's take a look at this. Let's say we have a business manufactures a product at a cost of 65 cents per unit. That's what it's costing us to manufacture it. And we're going to sell it for $1.20. Initially, we had to put up $10,000, so we need to know how much do we have to sell to break even. All right, so the total cost of producing X units, or total cost, is going to equal at 65 cents per unit, so 0.65x, plus we have that initial setup of $10,000. So that's the cost. Whereas our revenue is how much we bring in. So for every one of our units that we sell, we make $1.20. So we make $1.20 times however many units we sell. All right? We're looking for a break-even point, so we want to know when our cost is equal to our revenue. So we're 0.65x plus 10,000 that's a comma again, is equal to 1.2x. All right, so when we solve this equation, we can subtract the 0.65. We get 0.55x is equal to 10,000. So to find x, remember x represents the number of units that we have to sell. So when we divide, we get approximately 18,182. Okay, so the company must sell 18,182 units before it breaks even. Okay, well, the equilibrium point, here again, this is big in business, so I just want to kind of give you this definition. So an application that economists use is to analyze the market is with supply and demand. So a supply equation shows the relationship between the unit price and the quantity supplied, and typically the graph of a supply equation, which they call the supply curve. Okay, it makes sense, right? The typical supply curve rises. So a typical supply curve might look something like that because producers of a product want to sell more units at a higher unit price. Okay, so that's their goal. Whereas a demand equation, that shows the relationship between the unit price and the quantity demanded. Well, typically, for a demand equation, there is a decrease in the quantity when the price is more expensive. So a demand curve might look like this. Okay, so the equilibrium point there, if there's nothing else, no other factors to influence the market, then when it stabilizes, then we are looking for this equilibrium point. Okay, so we want to know when the demand is equal to the supply. So that is a definition that you're going to see, or you're going to have to work with quite a bit in this book, because we do a lot of business applications. So the equilibrium point is where the demand is equal to the supply. All right, and we'll try some problems like that in class. So hopefully that gives you a good breakdown of what we're going to be doing. All right, nice job.